Maybe a year ago, we were really talking about it was a year or half a year, I don't remember, but it was a year ago. And he's an expert in positron technology and positron science, and we developed some recent interest in utilizing positrons for characterizing point defects in uranium materials. And so we got to talk, and in the meantime, probably we can hopefully some follow-up projects or maybe spin-off of this interaction. But he's here today to talk about positron science and technology. Originally, Professor Mills got his degree, a bachelor's degree in physics from Princeton University in 1962, and then moved on to Brandeis University from 67 to 75 as an instructor and assistant professor. Worked at AT&T Bell Labs from 1975 to 2001 as a staff member, and joined the faculty of the University of California, Riverside in 2001, where he currently is. He also is the recipient of the Bell Laboratory Fellow Award from 1984, and the Fellow of the American Physical Society and AAAS in 2011. So with that, I'm excited to hear what's new in the positron science and technology.
Thank you for the introduction. So first, just so we can get off on the correct foot, everybody raise your left hand. Okay, you have to be left-handed in order to like antimatter. You all raise your the other hand. Well, anyway, never mind. Actually, half the people in my laboratory are left-handed, really, more than half. You develop an affinity for that. So I'll go through some positron history. You haven't heard about it already. So positrons began with the Dirac equation. It's been so long since I studied it, I probably couldn't say it right, but I think there was the Klein-Gordon equation, which was quadratic and everything. So it looked just like relativity for the energy. That's the Schrodinger, the quantum mechanics equation for a pion wave function or something that's a boson. It's got a quadratic term for the energy and momentum equals the total energy squared. But he wanted to make something that would work for electrons. And okay, go ask your teacher what it is. But the result was that he had to take the square root of the Klein-Gordon equation, and that led to the invention of spinors. So it also led to the fact that there were negative energy solutions, and he was very clever. He did what many theoreticians do. Things didn't work, so he made them work. He filled up all the negative energy states with electrons so that the positive energy states couldn't drop into them and disappear. So besides making the energy of the universe infinite, the thing worked quite well, and holes in the negative energy sea were identified as positrons or positive electrons. Nowadays, people don't bother with the negative energy sea thing unless you want to have fun with solid state physics, where you actually do get a thing like Dirac was thinking about. Instead, you say that there's an operator that makes plus ones and an operator that makes minus ones. That's about as far as my theory goes. Then Anderson discovered positrons and cosmic rays. You remember the famous picture of a curling beta particle in his, I guess that was a cloud chamber or something. And you have to know which way the magnetic field is. So the curvature was the wrong direction, and the bending of the trajectory was such that you know which way it's going. Get more curvature as it slows down. Anyway, then the Curie children found beta plus decay, and then Li and Yang invented parity non-conservation, which shook the world for a little bit, just like high TC superconductivity. in those days, everybody was doing nuclear physics, which is what all of you are doing, right? So at least I'm referring to your topic. Then positronium was discovered by Martin Deutsch at MIT, and he had 4 great, wonderful years where he made positronium and he magnetically quenched it. That means he turned a magnetic field on, and the triplets and singlets turned into each other and they decay faster. And he measured the hyperfine invisible, and he tried to make excited states, and that was about it. So, then we have Page and Heinberg. Too bad they discovered positrons had polarization when they were emitted. That's because parity is not conserved in the beta decay reaction. You probably learned that in your first year nuclear physics theories course, right? And then something happened in 1958. A character that, I'm calling him a character because he didn't behave like a normal physicist. He was a scientist, engineer working at RCA labs in Princeton, having nothing to do with Princeton University, but he decided he wanted to go up the ladder in the corporation. So he needed a PhD, and he called up and got somebody to say that he could be their PhD student. And why don't they try to make slow positrons? That means the positrons that come in beta decay, the ones that are free, well, if you pay for the radioactive source, but they're made spontaneously, they come with MED energies. In fact, there's at least one other way to make positrons, namely pair production. There's nuclear decay, pair production, and can't think of any others. Anyway, well, there's muon decay, but that's beta decay too. So, positrons are born with energies roughly equal to their rest energy, because you have to conserve momentum, you have to make something else to take up the recoil, and that's going to cost you quite a bit of energy. And at the same time, you have to make the positron, which has rest energy of half an MeV. So when you put in energy momentum conservation, you'll find you have a spread of energies. But there were already at that time, for 10 years, people had been using positrons to study solids. Positrons are interesting for studying solids because you can measure their lifetime in a solid, and that, to you, rightly sounds very dull. And it still does to me. But if you measure the lifetime, if you have a single lifetime, that tells you the average electron density around the positron, and you can learn something about your materials. There were many years where the concentration was just on the positron in the electron gas. But finally somebody found something useful. They found that if you take an atom out of its place in a solid, the positrons like to go there because it looks like a negative charge compared to the other places. And the positron would live longer because there's less electrons there. So if you have a material that has vacancies or dislocations or whatever else you can do wrong to a solid, impurities, then the lifetime will change. And instead of a nice, beautiful lifetime, my thesis advisor, Berko, had a student named Weisberg, and his job was to measure positron lifetimes in alkali metals. That's a perfect PhD thesis. I'm looking at the PhD students there because it's completely useless. And when you're done, there's nothing else to do. So, end of story. So, before him, people had measured lifetimes in all sorts of metal. They measured every metal. And they would always get, you're going to be able to see this? So here's time. Here's time. Here's number of counts. And you see a curve that looks like this. This is exponential log. So if you have a lifetime, it should look like that. But instead, it's got this tail. People would argue for hours at meetings. There were meetings every 3 years. There was a positron meeting. And people would argue. What is the tail? So Burkow decided to solve the problem. He gave it to his student Weisberg, and Weisberg said he was going to look at the alkali metals because they're simple, easy to treat theoretically, and the electron gas, or the electrons that the positron sees are mostly the free electrons in between the ions, and it made a very simple theory. People have done the theory, and there's no reason there should have been this tail. So he measured in the alkali metals, and he got this curve. Nice straight curve. Beautiful. And he plotted the energies, he plotted the lifetimes. That's the lifetime versus, lithium, sodium, cesium, beryllium, whatever they are. And they followed some nice curve like that. And the theory was right on. So that was the end of the story. But the same year that, or maybe it was the year after, about the same year that Weisberg did his thesis and got these perfect results, Burkow took a piece of aluminum and squished it, and he measured, well, now I have to go to the other thing. In these days, there were only two things you could measure with positrons: the lifetime and the angle between the two photons. As you probably didn't know, positrons in the singlet state, that means spin zero, opposite spins, but appropriate sign combination of that and that. You couldn't tell what I was doing on the recording. Appropriate combination of the two sets of spins that would make it spin zero. That's the odd combination. Anyway, the spin zero positron electron pair go into two photons. Two photons come off with left, left, or right, right. And the triplet positronium goes into 3 photons. Anyway, so in solid, most of the electrons annihilate into 2 photons because the annihilation into 3 photons is down by a factor of the Klein structure constant, which is what it costs you to make another dot in this Feynman diagram. So if I put another one here, these are supposed to be photons. This is the electron and the positron. These are vertices. To get 3 photons costs you another factor of Klein structure constant, which comes in at each vertex after you square it. So it's lifetime and angular correlation. That's when in a solid the 2 photons go off back to back, which they would if the positron and electron were at rest in vacuum. They would go back to back exactly. Don't you want to say exactly? Well, no, I think it's exactly if they were really at rest. Okay. So in a metal, the electrons are moving. The positron, believe it or not, the positron in some metals has like nickel has a 90 picosecond lifetime, but the positrons are thermalized after about 3 picoseconds. So practically all of the annihilations are with the positron in its ground state in the metal. So the funny thing about the positron in a metal versus electrons is that most of the electrons are around the nuclei. So they're way down in energy, and I mean in binding energy, but they're moving around really fast. But the positrons don't see them because they're repelled from the core. That means from the inside of the atom is positively charged. So mostly they see the electrons in between, and the positrons make a rather perfect, well, they interact mostly with these electrons in a way that gives you a nice projection of the momenta of the electrons, the momentum distribution. So for example, if you had a free electron gas, this is supposed to be 3 dimensions, and this is a sphere called the Fermi sphere. I don't know if you've done that before, but if you put electrons one at a time into a square potential well, in other words, no potential except at the boundaries, then it fills up with electrons. It's a ground state, first excited state, second excited state, etc. and then on to 10 to the 23 electrons. So what it ends up looking like is a uniform distribution of electrons in energy versus quantum number there. That, if you take this distribution of electrons and let the positron annihilate with it, it will give you a bunch of momenta, electron momenta, projected onto the angle of the two photons. So you've got two photons like that, and you've got some net momentum like this, and that gives you an angle between them, which tells you the electron momentum. This is MC, this is MC, and the angle between them tells you the electron momentum. And when you project them, when you plot those in 2 dimensions, it gives you a sphere of uniform occupation, like that. Of course, I'm only drawing the 2-dimensional projection of it, but it makes a lattice of quantized momenta in the solid. And if you, they can only measure by projecting this usually into either 1 dimension. You get a parabola. That's your assignment, is to show that the projection of this into 1 dimension is a parabola. Or in 2 dimensions, if you measure it carefully, you get a upside down sphere. Okay, so it turned out that a guy named Stewart measured all the metals in 1950 or something, 58 maybe. Every metal, he measured all of the 1-dimensional parabolas, and they look like this. So there's your parabolic part, which is the free electrons, and then there would be a great big tail like this, which is the core electrons. So this is theta, that's the angle between the two photons, and this is the number of counts. The experiment is done like this. You have a radioactive source, you have your sample, the source radiates the sample with positrons, and then you have a couple of counters out here behind slits. So these are like slits, one on each side. So this guy Stewart made this machine, and he pushed the slits together until they were about 1/10 of a milliradian. That's 1 millimeter at 10 meters, right? Very fine. And he measures all these things. Did it by hand. He would crank this with a screw or something, write down the number. The number was being counted by a clicky-clack thing, like they used to have for counting people going into a movie theater or something. Anyway, a mechanical counter would go click, 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 click. He'd write down the number, he'd turn the crank, go smoke a cigarette. People like to smoke cigarettes then. Write down the next number. He did it for, I think, at least 50 different elements. And they all look like this. So Burko noticed, experimental science is basically the process of setting out to do some boring experiment and noticing something that nobody noticed before, even though you thought it was going to be boring. So he found out that if he took a piece of aluminum, that he saw it off of a hunk of aluminum, it didn't look like this. It had big wings on it. Well, he discovered that the dislocations were changing the angular distribution. And then some other guy named Mackenzie was measuring lifetimes, and he discovered that if he took his nice aluminum crystal, which gave a beautiful exponential, then you would get a tail. And Mackenzie was the luckier one, because he plotted his results. He was varying the temperature. Okay? When he heated it up, it looked like this. So he had a knob to turn. Burko had no knob. He just put, well, he did have a knob. He put the sample into a vise and turn the vise 1 push, 2 push. Anyway, that wasn't sensitive enough, so unfortunately he got left out in the cold on this one. But Mackenzie plotted versus temperature, and he got, this is the number of ones that are in the bad part of the curve, and he found that this made an activation energy, what could be analyzed as an activated process. Okay? And he finds the activation energy, and that's why measuring the lifetimes was not stupid. So the positron development up to the time that I'm telling you had this frenetic activity, measuring all the lifetimes, measuring fantastic lifetimes, measuring the angular correlations, discovering positronium, quenching positronium, and then it sort of slowed down. But then Mackenzie discovered this, and Burke wrote his part, and people suddenly started to measure deformations and other problems with real materials. So now it took off, and there's a complete industry worldwide. Now there's two types, or maybe more, of positron scientists. There's the ones that actually want to do something useful. They can do something useful with 2 little counters, which you can make for a few $100s, and a piece of sodium-22, which costs, $60 a millicurie, 60 cents, 6 cents for a microcurie or something. Anyway, nothing. The source is practically free. You take your 2 pieces of material, put them together, measure the lifetime as a function of temperature, and you can tell all sorts of stuff about it. And they spend hours at conferences arguing about whether zinc oxide, which is, who would have thought that the stuff they use for babies' diapers would turn out to be the most fantastic spintronic material. Did you know that? Zinc oxide? I didn't know. Single crystal zinc oxide. Who knows about zinc oxide? Wow, I've done you a favor. I don't know anything. But this stuff is, do you know about the topological insulators? One guy has heard about them. Anyway, these things are the most fantastic solid state things that's ever happened. And I think there's an issue of Physics Today or something that's devoted to the fact that solid state physics has completely eclipsed all of the rest of physics. And anybody who's not doing zinc oxide or tantalum selenide or whatever, quantum Hall effect doesn't get any money anymore. Anyway, so that's this business of being able to analyze something about a solid was really important for a variety of reasons. Now, unfortunately, the positron people tend to cling together, because they all raise their left hand when you say raise your right hand. So they don't always keep up with the actual hottest stuff. But right now, everybody is working on zinc oxide. And so all this beginning stuff, which was pedantic and scientifically interesting, sort of, actually turned into something really useful. Okay. Now, the next useful thing that happened was in I said this guy, Cherry, made some slow positrons. I didn't say what they were. First, I had to tell you why they weren't slow when they were born, because they're made with kinetic energies equal to their rest mass, roughly. But to do these nice experiments, the one class of which I told you about, the positron is slowing down in the sample of interest. And it slows down fast enough. Why? Because the positron has a range in a solid of about, 10 microns or something. Let's make it 100 microns. And how far does it go? How far does the positron go before it stops? Well, it's going at the speed of light. How long does it take? Okay. So the speed of light that's meters per second. And I divide by meters, no, I divide this number, 100 microns, divided by C will give me a time, right? This is the extent of my theoretical ability. So this is 10 to the minus 4 meters divided by 3 times 10 to the 8 meters per second. I can't believe it. A third of a picosecond? Okay? So that's how fast a positron slows down in the material. That's why virtually all of the signal that you see is from the stopped positron and the moving electrons. That's why you can get this solid state information unambiguously. Yes?
What slows down the positron? I would think that if it interacted with anything, it would annihilate it.
You might think that, and I'm glad you asked the question. The positron slows down by scattering off the electrons. Okay, here's an electron, here's the positron. But the cross-section for scattering is way bigger than the annihilation cross-section. I guess I could draw a Feynman diagram that has one thing, and the annihilation has two things, vertices, right? That's why. So the annihilation is 100 times less likely than scattering. Something like that. Okay. So the trouble is that until this time, the sample was also basically the source. Like you go to an accelerator is your source, and then you put your sample in it. But in this case, the source and the sample were the same entity. So in 1950, before even Martin Deutsch's experiment, a guy named Medansky figured out that it would actually be nice to be able to take the positrons away from the source and put them into another sample in a controlled way. So he was really foresighted. He thought that some of the positrons coming out of a piece of material, you have your source, you put the positrons into the material, and some of them might be coming out with thermal energy. If the material had a negative affinity, it would. And there are some materials like that, named tungsten, single crystal, diamond, copper, lots of things have a negative affinity for positrons, and each of them makes what we call a moderator. So this was the dream of Medansky and Rossetti in 1950, but sad story. They made a perfectly good machine for doing this experiment. So they had a little copper 64 source, I think. And then they had a material that they put in front of it. And then they had a solenoid. That's a magnetic coil like that, right? It goes like this. And if there were any slow positrons, they would have been caught by the field and go down to the other end where they had a piece of metal where the positrons would hit and annihilate, and then they have a detector to count one of the gamma rays. So they did their experiment and said they saw less than 1 in 10 to the 5th positrons were coming out thermalized. So this guy, Cherry, he didn't even know about Medansky's paper because he was an electrical engineer. Sorry, no, he was an electrical engineer, but he wasn't into the physics. But he published his paper in which he got 1 in 10 to the 8 positrons were coming out of a piece of chromium as slow positrons. And he got about, 10 positrons per second. That was the first positron beam, the first time when you could have taken positrons of a known energy, put them into something, and learned something about the material alone, without the complications of the source. Anyway, Cherry, this guy, last on the list here, second to last, didn't publish his results. He wrote his thesis which a few people knew about, but it wasn't widely known. So people went on, and some people decided to make slow positrons other different ways. And finally, in 1972, this guy, Cantor, discovered the first reproducible positron moderator with enough intensity, enough likelihood of making slow positrons, so you could actually do something useful with it. Before that, there were just a few, like 10 or 20 per second. And it was, you had to sit there for days. Like, they were interested in measuring gas, the cross sections for positrons scattering off gas molecules, which was a, that became its own little side field and is still dribbling along today. People are still measuring positron cross sections. It's gotten a little more interesting. Anyway, it was going so slowly, you would have to wait a whole day for one energy and then change the energy and measure another one. So that's how these guys, Coleman, Griffith, and Halen. Coleman was the postdoc. Griffith and Halen were the big professors telling him what to do. And you professors don't do that, right? At University College London, and they called up Glenn Rolig and said, who you got for a good student? And it was Cantor. He went over there and joined the group in about June 1972. And there they were in the middle of measuring the cross-section for helium scattering of positrons. And they were every day. They'd have to go eat their tea and crumpets in the tea room, and they'd come in and change the potential on the voltage. 19 volts today. We're going to do 19 volts. And they go home. And they come back the next day. And Cantor had been reading that people had made lots of positronium from powders. That happened in 1968, lots of years, several years before this. A guy named Paul Lan from Paris found that if you stop positrons in porous or powdered silica or powdered aluminum, you can buy these in jars, magnesium oxide powder. They made lots of positronium. And Cantor thought, wow, if we used a layer of powdered, one of these powders, it might also be making positrons as well as positronium. So he suggested that to his colleagues. And they said, well, that's an interesting idea. Let's take that up during tea time next Friday. They didn't come in on Saturday. We'll take it up at tea time. And they did that for a couple of weeks. And every day, changed the voltage. 21 volts. Some more. 22 volts. Okay, so then Cantor got an idea. He was going to come in on Saturday. And this was the day when a vacuum system, you probably all worked with vacuum systems. They got knife edges and ion pumps, and they're really complicated, held together with flanges with thousands of bolts. But in those days, everything was made of brass, and you just undo a clamp and the thing would fall apart. So it was nothing to take the vacuum chamber apart. All there was probably a diffusion pump with a valve and a little brass chamber and a magnetic coil and then a detector, and that was it. Very simple. So he popped the source out, took the other people, they're no dummies. They made a moderator out of gold. At least they had some idea about what to do. So here's their sodium-22, which is on a little pellet or something. And then they put veins of gold like that. No, they didn't. Sorry, they didn't do veins. That was Cantor's idea. They put it inside of a cylinder lined with gold. Oh, can't do that these days. This is a gold cylinder. I think it was gold foil, but still. Anyway, so their idea was that the positrons would hit the gold and get moderated. They didn't tell anybody how, but that's what they made. They already had the idea of bouncing off something. So Cantor made something much more bouncy. He made vanes that look like this. He called it a Venetian blind. Do you know how to make a Venetian blind? He used to tell me, and then you go like that. Anyway, I wasn't a Venetian. Anyway, he would make a Venetian blind. He made a Venetian blind, and when it was not in this place here, he held it over a burning magnesium ribbon. You ever try to burn magnesium ribbon? No, it makes a very bright light. Don't do this at home, children. Anyway, I guess maybe he had welder's goggles on. Because of this incident, when I left Brandeis University, where Carl Cantor was, the first thing I did when I got to Bell Labs was buy a roll of magnesium ribbon, because the moderators hadn't gotten any better since then. So I wanted my roll of magnesium. I kept it since 1975 until about 2015. How many years is that? Not so many years. And I wanted to wake my class up in Physics 2. So I can't remember what I did, but I said, now watch this. And tried to light the magnesium ribbon with a blowtorch, blow it at Bunsen burn. It wouldn't burn. It wouldn't burn. Do you know what happened? It oxidized. It's amazing. I guess if I'd melted it, it would have burned. But anyway, so the next, after all the booze and stuff, the next day I came in, I scraped it down to bare metal. Anyway, this was brand new magnesium ribbon. You burned it on there, it gets coated both sides with magnesium. And suddenly the count rate went up a factor of 100. So they could do it in a minute what was taking them 2 hours. So he sewed it back together. Nobody could have told that he'd done anything. Just the same dirty old brass vacuum system. Put it back together and started counting again. They were furious. They came back Monday morning after their nice lazy weekend and called him on the carpet. What have you done? You ruined the experiment. We've taken data for 35 days. Now, we can't do anything with it. And Candace says, well, you could repeat the experiment this afternoon with better statistics. And then they were happy. But then they realized that they were in the process, they weren't very vicious about how fast they turn out the research. So they have made their moderator twice as good by providing them this gold thing. And maybe 10 times, I don't know. And they were writing it up. But they realized that this discovery had to be written up immediately because it was really important. I mean, this discovery changed the theoretical concept of slow positrons using the sample being different from the source into a reality. It's on the low edge of reality, but it's enough count so you can do something useful. So then they were really angry because they realized that Cantor would have to be on the paper, and it was their policy, their own fault, that they put the names in alphabetical order. Guess whose name was first? Rightly so, but they've done a lot of development, you know, setting up the beam, getting the money to pay their summer salaries and stuff. Anyway, so they were angry again, but they calmed down because they realized, well, let's submit our paper, that means Coleman, Griffith, and Halen's, not Cantor, because he wasn't there when they developed it, our result from the gold cylinder. So they were happy. They wrote it up. And they let Cantor write up his version. Notice they didn't call it Discovery of Fantastic Positron Moderator. It was called Scattering Cross-Section of Positrons in Helium. You have to be have great insight to be able to figure out that it was about the moderator. Anyway, so they sent the papers off. They sent their paper a week early, and then they sent the Cantor paper. And their paper dragged on and on with the referee. You don't have enough counts. You didn't know whether the gold was clean or not. But Cantor's paper sailed through, and it came back saying, this has got to be a letter. This was in British journal that James's B. Letters, or whatever it was. So his paper came out in September, just a month or two after it was submitted, maybe just 1 month. But the other paper dragged on and dragged on. Finally it came out in January. So it says 1973, where Cantor says 1972, and they were furious again. Anyway, by that time Cantor had left and joined Steve Berko at Brandeis, which was the reason I'm standing here today, being able to do anything in positrons, is because Cantor came and changed me from being a source as the experiment into a being person. I have no idea what time it is.
It's 7 minutes to 5.
And what does that mean?
Yeah, 7 minutes.
Well, now that I've gotten halfway through the introduction. So this talk is just going to be the introduction. Anyway, 1974, that's 2 years after Cantor joined Berko at Brandeis, he discovered slow positrons on a metal make positronium in vacuum. It's not a big deal, you wouldn't think, but was a big deal then, because it was the first time somebody had actually done something with enough counts to be really sure and make something nice. And then next, we were able to do the experiment that I'd been working on, trying to make excited states of positronium, because then maybe you could do atomic physics on and look at the Lamb shift of positronium, which was really interesting in those days. But I was looking with my detectors at the very spot where the fast positrons were going in, so there was tons of background. There was no hope that I would ever be able to do it. But Cantor did it this way. We put a detector next to an optical detector next to the positronium forming target, and we could see that there was Lyman alpha radiation. And then I was able to turn on some microwaves and measure the fine structure. So that was the beginning of nice research. And the result of it was that Phil Platzman from Bell Labs called up Steve Berko and asked, which of these characters should I hire? And for some reason, I was chosen. So I left them, which was really sad. It's really terrible to leave an operating experiment. But on the other hand, it was a good thing, because you can sometimes go faster if you work by yourself. But the next notable thing was exciting the 1s state of positronium to the 2s state by 2-photon excitation, which is Doppler-free and is now commonplace. I don't know if it's commonplace amongst nuclear engineers, but there's a guy called Ted Hench who has measured the hydrogen 1s to 2s interval, which 1s to 2s is forbidden for 1 photon, because 1 photon has 1 unit of angular momentum, and 1s and 2s both have 0 angular momentum. So you need 2 photons to excite it, and if they're in opposite directions, then you can excite it Doppler-free, first order. So Ted Hench has measured this interval to a part 10 to the 18 or something. The line width is terrifically narrow. It's about 10 hertz. And if you measure carefully, you can split that line to much narrower. And at this moment, I believe still raging is a little argument about whether the same physics is applying to a muonic hydrogen. So people have measured spectra of muonic hydrogen, and it all comes down to the charge radius of the proton. So protons are really nasty things. They're not point charged just like positrons. So there's a huge correction. Here's the Coulomb potential, going like 1/bar. And if you go close enough, the proton looks like a little fuzzy ball of charge. The easiest thing is to say it's a shell of charge, then I don't have to do anything fancy. And so the potential cuts off like that. And the theoretical 1s, 2s interval, which starts with 1 Rydberg times 1 plus alpha squared plus blah, 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 all those alphas, it's meaningless because you've got to correct for this charge radius. So the error is going to be something like the charge radius of the proton over the Bohr radius squared times a Rydberg or so. Anyway, it's smaller than that. Anyway, there's a big correction, but in positronium you don't have that correction. So it's nice if you just want to look at the alphas, but now people are looking at what's wrong with the proton. That topic is the subject of my next lecture. Wait a minute. Wait, you can't stop me. In, 50 years before, 60, whatever years before this, there's a guy named Lamb. You may have heard of the Lamb shift. Willis Lamb at Yale. He measured the Lamb shift, which is there's a shift between the 2s and 2p states with some subscripts that I can never remember, which is 0 exactly in quantum electrodynamics. He measured it, and it's 100 and something, 180 megahertz. I don't know what it is. I can't remember what the number is. Maybe it's gigahertz. 1 gigahertz or something. He measured it. Now the trouble is, this line is from a 2p to a 2s and sitting above the 1s ground state. And ordinarily this makes a transition called Lyman alpha. You know what that is, right? It's a 2p to 1s radiation from hydrogen. So it's Lyman alpha. And the lifetime is 1.5 nanoseconds. So the line width is 100 megahertz. So I've changed my mind here. This is about 1 gigahertz. I can't remember the digits. So the line width is 10%. It's a big, fat, ugly line. Right? That's, I don't know what the full width that. I guess it's 100 megahertz. And he quotes it in his paper. This triumphant paper. Because they have all the factors for what it ought to be, because they use quantum electrodynamics, not just quantum mechanics. And so he measures it, and his error bar is 0.1 megahertz or something. And he says the error bars are actually 5 times smaller than that, but just to be safe, I'm making it a little bit bigger. So then people use this backwards to calculate what the fine structure constant is. So the fine structure is 1 over 137.0386.07, I don't know what it is. Anyway, that's not the number he got. It was a different number. And people were wondering, why doesn't this atom work? Why doesn't that transition work with this fine structure constant? So finally, one day in 1980, somebody invented the quantum Hall effect. You know what that is? Only one guy knows everything here. Quantum Hall effect is, the Hall effect is you put a magnetic field on something. This magnetic field, and the electrons tend to go off to the side. That's the Hall effect, making a plus minus, I'll have to sign all of them, I'm sure. Anyway, you get a voltage across it called the Hall voltage. But then, if you do it with low density two-dimensional electron gas, and plot the resistivity, it looks like this. I don't remember whether they go to 0 or don't go to 0. I think it's like that. And that's called the quantum Hall effect. And von Klitzing is the guy that invented it or discovered it. He got the Nobel Prize. Anyway, he published his paper in Phys Rev Letters. The Phys Rev Letter comes out, and meanwhile, the connection in here is Platzman for his work, for his thesis work with Richard P. Feynman. Platzman and Iddings had calculated something that required the fine structure constant in order to get some proton form factor or something, and it didn't agree. And he called up, at the time, he called up Lamb at Yale and said, maybe you might have made a mistake. He was just a global graduate student, sorry. And Lamb said, no way. I did my experiment, well, maybe he didn't say perfectly, but with the utmost care. And so that was about 1958 or something. So now, 22 years have passed, and von Klitzing comes out with this Rev letter, which has the quantum Hall effect gives you directly a fine structure constant, E over M. There's no H, you have to put that in yourself. And so a couple of days after the Phys Rev letter came out, Platzman gets a phone call. It's Willis Lamb from Yale. He says, Phil, how would you like to come and give a colloquium? No mention of von Klitzing. So he goes to Yale. And unfortunately, Platzman told me this story when he was very sick. And I wrote it down in the crudest form. I'm not exactly sure of the precise. I didn't actually appreciate the story until a couple years later after he died. But anyway, I believe what happened was this was sort of Vernon Willis Lamb's way of apologizing. Let him give a nice talk, and then he took him out for dinner as a reward. Dinner at Maury's, that's supposed to be some Yale in joke, where the Whiff and Poofs thing or something, and they drink a large pot of wine. Anyway, so I think I'll end the story at the beginning of the lecture I was going to give.
Well, you did promise us a slow positron lecture, and you delivered that. Positron lecture. We'll meet.
So, if there's any questions, I'll give you the second half.
What's the half-life of
For 1/8 of a nanosecond, triplet states 1/7 of a microsecond. The lifetime is much longer for the triplet because that's my third photon.
Absolutely.
No questions? If not, then I really hope there will be a follow-up talk to this very fascinating introduction. So I would like to see the experimental part of this and learn what the current experiments is ongoing in Riverside, hopefully in next semester. Fascinating. Thank you.